afternoon, everybody, and welcome to our final webinar. Thank you for joining us today. First of all, I would like to thank you all for your very kind messages in the wake of last week's very tragic events. Thankfully, all of us at ESCWA are okay. But thank you very much for the messages from across the region and beyond, very much appreciated. Secondly, also because in the wake of the events, we may be having some internet challenges. If we do and lose connection, we will do our best to restore the connection immediately. But in the worst case scenario, if we have trouble, this will be available as usual on demand from our website. Again, this is our final module of this webinar series. Today we're going to shift a little bit. We've been working all along with climate data sets, and today we're going to be talking about vulnerability assessments, which takes into account climate data sets as well as socioeconomic data. Today we'll be discussing what are vulnerability assessments and why are they useful. They can be applied at the regional, basin, local, and also sectoral scales. We'll be discussing the integrated methodology for vulnerability assessments, what we applied in RICCAR, and how you can apply a vulnerability assessment for your own study that you may be interested in. We'll discuss how to aggregate data. To do this, you will need geospatial data sets, and we'll discuss how to obtain data sets and aggregate those in order to develop the vulnerability assessment. And to do this, we'll be using several integrated mapping tools. This is perhaps one of the most GIS involving webinar modules we've been presenting today. Thus far, we've been primarily working with NetCDFs, which are their own set of tools. They're the multi-dimension tools we've been discussing, but we'll be using all sorts of different tools to be able to conduct vulnerability assessments. So for those of you who do not have ArcMap availability, feel free to reach me offline and we can see how you can use data sets and tools from GIS, whether it be QGIS or other mechanisms to be able to conduct vulnerability assessments. But again, we're using in this context ArcGIS to be able to evaluate and develop vulnerability assessments. And sorry, another announcement. As usual, Joelle, my colleague, will be moderating the session, and feel free to enter any questions you may have into the chat. And she will be moderating those, answering some online, and the remainder will be answered live at the end of the session. So again, we've been focusing all along on the impact assessment side, which is this area highlighted in blue. We took, we looked at, there's global climate models. And what we've been working with is the downscaled regional climate models. And both of these take into account different scenarios known as representative concentration pathways, or RCPs. And from the RCM outputs, we did further analysis, and we talked briefly at the end of last time's session about the regional hydrological modeling outputs. So we took things one step further. But all of this is incorporated as part of what we describe as the impact assessment. And if you happen to look at our report, this is all detailed in the first half of the report. The second half of the report takes it one step further and takes all these outputs from the impact assessment to incorporate into a vulnerability assessment and integrated mapping. What we did, this is not our own methodology. We adopted a methodology for vulnerability based on IPCC and their fourth assessment report. Their fifth assessment report describes it a little differently, but what we feel more suitable for this region and continues to be popular is the definition of vulnerability from the fourth assessment report, which takes into account socioeconomic factors and environmental factors such as land degradation, crop yield, population demographics, and coastal erosion, as well as the climate changing hazards, which most of us who are in the scientific field tend to think of climate hazards as the, not necessarily the sole, but definitely a strong contributor toward overall vulnerability. So it includes, climate hazards, of course, including changing temperature, variable precipitation, but it also includes hazards like sea level rise and forest fires and other related hazards. Of course, we did not evaluate sea level rise for our evaluation due to data limitations, but I mean, this is just an example of various climate hazards. And again, consideration of socioeconomic factors. And on the flip side, these are the coupling of climate hazards and socioeconomic and environmental factors are kind of what entails the total impact or potential impact upon a system. Adaptive measures are the counteracting these impact factors. Adaptive measures may include information dissemination, improved infrastructure, funding resources. So these are some examples of adaptive measures that can be taken to overcome these impacts. In further detail in our context, we take this framework. So exposure, which are these climate hazards and climate related hazards. Sensitivity, which incorporates the land use, the population demographics, and other factors that makes a system more susceptible to climate change. And the combination of these two is potential impact. And as I mentioned, the opposite of potential impact, to overcome potential impact, is adaptive capacity. It's the mechanisms and willingness to overcome these impacts. So vulnerability is the difference between potential impact, which is the combination of exposure and sensitivity, minus the adaptive capacity, which is how we define vulnerability, and which is conjunction with the IPCC fourth assessment report. Here's another way of looking at it. So potential impact is increasing in this direction, and adaptive capacity is increasing in this direction. So the higher the adaptive capacity and the lower the potential impact results in low vulnerability, which we kind of generally regard in when we map this as in green colors. The lower the adaptive capacity and the higher the potential impact results in high vulnerability. And of course, somewhere in the between is moderate. So that's one way to look at it. And if you look at our maps, which we will start to look at later, we follow this same color mechanisms, where we define low vulnerability in green coloring, high vulnerability in red coloring, and moderate vulnerability in yellow coloring and colors in between. What's nice about vulnerability assessments is they can be conducted at any scale. Now, of course, there's a little bit of a weakness as well, because they are only relative to the spatial and temporal scale specified. So if you happen to look at our RICCAR reports, we have vulnerability assessments for the Arab region. However, these results are only relative to the Arab region itself. If we were to compare on a global scale, the results may be very different and very potentially worse. So that's one thing to bear in mind when you look at vulnerability assessments. Quite often, vulnerability assessments are only done at a very, very local scale. They may be done only at a basin level or country level. And again, they're useful for that particular discussion, but when it's being discussed at a larger scale, when it's being compared to other regions, other hydro basins, etc., the results are might be very different. So you need to bear in mind it's only relative to the spatial and temporal scale. What's nice, vulnerability assessments can also be looked at very small periods. It can be looked at for a specific climate event, perhaps a extreme event, a flood, a major flood, a cyclone occurred, and you would like to conduct a vulnerability assessment to assess the impacts for that specific event. Can be done. Or you can conduct a vulnerability assessment at a much larger scale and a much larger time period to assess impacts on climate change, as what we did for RICCAR. Again, we did it for the entire Arab region at and a multi-year time period. So we looked at it for end century and mid-century and compared those to the reference period. So again, you can look at it for a very large scale, very long time period, or a very, very short time period and small area study. To review, so vulnerability is measured using exposure, sensitivity, and adaptive capacity indicators. And these indicators are geospatial. They're from GIS data sets. And we do this because ideally at the end, you will present on a map. And what's nice about the map, it conveys a very clear message to end users. I mean, you know, you may have government officials who are less familiar with climate change, you know, and have trouble necessarily grasping concepts. And so it conveys it visually, which is a very clear message, and it clears areas of hotspots that may be most vulnerable to climate change impacts. It is a very effective tool to convey in reports and for messaging purposes. We will be covering quite a bit during this module. I know it's kind of tough to do everything in the hour session we have. Usually we conduct our webinars, our training on vulnerability assessments over the course of a day or a day and a half. So we'll be covering a lot today. What you can do is review these documents. We have a training manual, which is a general training manual on vulnerability assessment methodology, which is available currently from the RICCAR website under knowledge resources. And there is also this technical note, which details what we did for RICCAR itself for the Arab region, which has some, it's not only for transparency in our methodology, but it's also some somewhat lessons learned and some aspects that are unique to the Arab region for consideration. So this is the one on the left is a much more general for regional for vulnerability as a whole, and this one on the right is more for application. The application we did at the Arab regional level. We also have available on our website from RICCAR and our knowledge resources is an application which we conducted in the wake of RICCAR and for the Lebanese agricultural sector. So that resource is available for your interest, and it may also give you ideas of how you can conduct your own vulnerability assessment, and either on your own, or of course we're available to assist if as need be. So with that, where do we get these indicators? Indicators are available. First of all, the ones we use for RICCAR are available free of use from the Regional Knowledge Hub data portal. So if you want to use those, they're available for your, for as you see fit. Again, these indicators on the Knowledge Hub data portal are for a regional level. So in many cases, the spatial scale is quite large. In many cases, particularly for adaptive capacity, they are at country level. but they're definitely available for use. So some of these other resources, especially at a smaller scale, may be more useful for you. The World Bank most recently launched a Maastricht Water Resources Portal. Here is the website, which entails, these are also tend to be large-scale data sets, but they're available for use. FAO is fantastic in terms of geospatial data, if you're interested. There is a GeoNetwork, which has been long available. Here is the website, and that includes many large-scale and as well as small-scale data sets that you may find of interest. FAO has also recently launched a geospatial platform that they call Hand in Hand, and this is very new, but it has some exciting things coming to it. So it's not fully populated with data, but you're available to log in and look at geospatial data sets that you may see fit. And you also can see if they are not populated with data sets at this current time, you'll be able to see what's upcoming. So this is another resource. You can develop your own data sets from remote sensing, which are certainly very helpful. And there is also remote sensing data sets that are already developed, like the normalized difference in vegetation, which is a common data set to use. And since many of you also work in geospatial data, you may have your own GIS data sets for your governments and your research institutes. So any of these can be very valid indicator sources that you can use for a vulnerability assessment. When you look at selecting indicators, there are a few things to bear in mind. Of course, the relevance. I mean, you want an indicator that's relevant to your environmental system being studied. If you're talking about water, you're probably considering precipitation, runoff, the water resources themselves, the availability of water resources. And you also can consider demographics like people. People are water users. Agriculture is a water user. But you may not want to look at indicators that are not relevant. So you need to bear it in mind what your system being studied. When you go into developing vulnerability assessments, you need to always consider your system that you're evaluating. You would not blindly just start a vulnerability assessment. You need to consider data availability. One of the challenges we had for RICCAR is obtaining data for the entire Arab region. I mean, there are some Arab states that data is very limited and presented challenges for us in terms of data availability. So ideally you would have data geospatially for the entire study area. If you happen to have a data set that you are really think that is important, you could either develop a composite indicator, but doing those methodologies is not preferred. It is better to have a data availability already set for your entire study area. The indicator needs to be able to be measured, quantified. Quantification is not necessarily always numerical. It may be descriptive, such as land use, but it could be, land use can even be quantified if you're considering your environmental system. Areas that are prone to flood, areas that are more vulnerable for flood may be urbanized, impervious areas, and areas that are less prone to flood may be very rural areas and areas that are not used for populations, not necessarily used to a lesser extent for agriculture, etc. So, for the most part, indicators can be quantified one way or another, even if it's descriptive data. Your data sets should be homogeneous. They should be from the same data source and time period. Again, in some cases, you may have to develop a composite indicator. And if you must do so, it should be more or less homogenized to have the same methodology to develop. So you're comparing across your area study uniformly. And lastly, your data set needs to be reliable. Oftentimes there are data sets that are out there that may be developed by certain research institutes that may induce some controversy, and you certainly do not want to do that. So you should have a data set that's reliable, one that's well vetted from a recognized, reputable organization, whether it be a UN related organization or a reliable institute. So you should have definite confidence in your data sets that you are utilizing. Indicators will tend to have a tendency to have a varying magnitude in units of measurement. Precipitation is, of course, in millimeters per month. Temperature is in degrees Celsius. Population data sets are in persons per square kilometer. So they will have different units of measurement. And then that presents challenges when you aggregate data. So to overcome this, we need to classify using a unitless common scale. Because we classify data sets, oftentimes if you have data sets that may have some similarities, they may be from different sources, may be different data sets overall, but when they're classified, they more or less classify similarly. You know, more indicators is not necessarily a good thing. You can definitely convey your message using fewer indicators. So that's one thing to bear in mind. But again, we'll classify indicators using a common scale, such as from 1 to 10. There are many, many ways to do normalization and classification. You could first of all use it in GIS, and we're going to look at that shortly. You can classify using expert opinion. This is particularly useful if you are classifying data that is descriptive. So expert opinion may be involved to determine what areas are more vulnerable. Again, if we're looking at land use, for example, areas that are more vulnerable that are impervious versus an area that is very rural and full of vegetated areas might be classified very differently. So expert opinion can be used primarily for descriptive data, but it also can be used for data sets that are numerical as well, but if need be. You could also classify based on a reference scale. For example, total renewable water resources can be compared to the Falkenmark water stress scale. So, and that kind of has different ranges of areas that are water stressed. So this is a reference scale. So that's one mechanism you can classify. And what is probably the most common method is the min-max normalization. So we're going to look at that as well in a bit. So again, to use in GIS, we open the Spatial Analyst tools, and we use a tool called Reclassify, which is under Reclass. And here's the same tool in Arabic and the same tool in the French version of GIS. For those of you, I've had a lot of questions about how to open Spatial Analyst. You need to open Spatial Analyst by activating the extension, which is found under Customize and Extensions. So that needs to be turned on. And if you have the license, if you don't have the license, feel free to message me offline and we can see how to resolve that. So once you open the tool, it will look something like this. It will look, you'll have a similar window in either the Arabic and French versions. And what we do is it will automatically show up and it will automatically classify. But we can reclassify these values. You see the ranges and the classifications from 1 to 10. We click on this button, Classify. Once we do this, a window similar to this will show up. And at the top, you select your classification methods. And there are many methods of classification you can select from, as you see here. So manual is user-defined intervals. You can define it based on whether if you want to use a reference scale, etc. You can manually define your breaks, your intervals of your classes using manual interval. Equal interval is exactly how it sounds. It subdivides the attributes into equally sized ranges. Defined interval specifies an interval size to define a series of classes with a range of values. Quantile is a statistical analysis to an equal number of entities, and it's best used for linearly distributed data. And you can look in more into GIS about quantile distribution. There's also a method called natural breaks, which is also known as the Jenks optimization method. And classes are determined by the natural groupings of data inherent to the data set. And lesser common utilized methods are geometrical interval and standard deviation. We had a tendency for RICCAR to use these top four, and we justify, and if you happen to look at the Regional Knowledge Hub data portal and look at the indicator data sets, there are fact sheets, and for each of these indicators, we selected the method. We denote what method was used to classify each of the data sets and why that method was selected. For the most part, we evaluated each indicator individually and had a peer review to agree what was the best suitable methodology for classification. So these methods can be done in GIS using the reclassification tool. So once you select a method, it will automatically reclass. You'll see the range of values. So for example, classification number 1 is a range from 0 to 335. Classification 2 is a range from 335 to 1,343, etc. Again, here I mentioned that expert opinion is best suited for descriptive data such as land use. Reference scale is best used for comparing to a known scale, such as the Falkenmark water stress indicator. And then lastly, min-max normalization, which is using the equation here. It basically compares the value of the data of that particular data point, comparing to the minimum value of the entire range and the maximum value of the entire range. It is noted that sometimes datasets may be skewed. It may have a wide range of values that are not necessarily would be on a bell curve, for example. It would be they have a skew to them. For example, if you happen to look at FAO Aquastat data for total available renewable water, it will have very small values for some countries like Qatar, and very high values for other countries. So in that case, it is better to take the log, do log transformation of the values before it is normalized. So you'll need to evaluate each data set and see if there is some skewness to them and consider doing log transformation. Once we have all of our indicators, we will assign relative importance to each indicator. And indicator weighting is a very debated topic in terms of vulnerability assessments. So it presents some challenges. We'll go over indicator weighting a little bit more on the next slide. What we did for RICCAR, because there are so many indicators that were used, and we wanted to have some balance between each of our indicators, we classified our sensitivity and adaptive capacity indicators into groupings which we call dimensions. So for sensitivity, we had about 8 indicators that are related to population. We had about 10 indicators that we call them natural, which are related to the natural environment, and only a small number of indicators that are related to man-made, the man-made environment. So we wanted to have each of these facets be equally considered, so we grouped them into different dimensions. This is just our suggestion for RICCAR. For those of you who may be evaluating a vulnerability assessment at a very localized scale, may only have 2 or 3 indicators or a very small number of indicators that are related to sensitivity. And in those cases, you don't necessarily need to group them into 2 dimensions. But if you happen to want to use a lot of indicators, several indicators, you may elect to group them into different dimensions. So that is up to you, depending on your particular needs. For adaptive capacity, we grouped the indicators into 6 different dimensions: knowledge and awareness, technology, infrastructure, institutions, economic resources, and equity. And then infrastructure was further subdivided into groupings which we call pillars, and that considered energy, water resources, environmental infrastructure, transport. So that was further subdivided, but again, we grouped our adaptive capacity into these 6 different dimensions. And again, if you only have, a small number of adaptive capacity indicators, these different dimensions may not be necessary. So again, it depends on your particular needs. So for weighting, there are many different methods to select weighting, and the weighting will have a significant effect on your results. So it's very important to carefully consider your weighting scheme. And to get a step further, you should consider 2 different weighting schemes and do a sensitivity analysis to compare your chosen method and justify your chosen method. I'm not going to go into the different approaches in detail, but here they're listed here for your own reference. What we did for RICCAR is we had a participatory approach. We sent out surveys to experts from across the region working in the field and had them rank different facets of vulnerability, potential indicators on their relative importance. It is common to simply approach weighting by weighting indicators equally, and weighting equally is certainly a valid approach, but it is not necessarily the best approach. So it should be justified ultimately if you elect to do equal weighting, because equal weighting, quite honestly, is a bit of a cop-out, so to speak. So it's not ideal to use equal weighting. So make honest attempts to seek out these different methods to weight your indicators. Once you have all of your indicators determined and classified and weighted, you will then aggregate each of your indicators to ultimately determine vulnerability. The most common methods to aggregate are arithmetic aggregation, and you'll see the resultant formula here. There's the weight of a given indicator and the indicator themselves. So you'll multiply the weight times the indicator and subsequently add all of your indicators multiplied by their weighting respectively to develop a composite. This has a tendency to have a weakness in terms of full compensability. Some performance of poor indicators will be compensated by sufficiently higher values of other indicators. And this method is not ideal. And in order to become this full compensability, it's preferred to go to partial compensability, which will not compensate as much. And this is the method that's more commonly used, and it was used for RICCAR as geometric aggregation. So what is done is you have the indicator raised to the power of its weight, and ultimately all of your indicators with their weight as the exponent will be multiplied together to aggregate to develop your composite. So you'll have all of your, you'll aggregate at each level. You'll have each of your, well, level 1, maybe all of your indicators for each of your exposure, sensitivity, adaptive capacity. If you happen to have a lot of indicators and choose to use dimensions, you will then aggregate at your dimension level, and then you will ultimately aggregate your 3 components at the very end, whether it be exposure and sensitivity to determine a potential impact, and then your adaptive capacity on the flip side. So you'll ultimately aggregate each level. If we look at this next slide, all of this is becoming a little clearer. This happens to be an impact chain. Ideally, you would develop an impact chain at the very, very beginning. You could use it as a brainstorming tool. If you are looking at a particular sector, whether it be water, agriculture, forestry, you would have a team assess what factors, what indicators would be most relevant to that particular sector. So we select exposure indicators that are relevant, we select sensitivity indicators that are relevant, and we select adaptive capacity indicators that are relevant. This happens to be the impact chain for RICCAR that we used for availability of water. So you can see all the indicators we used. After these indicators, you'll see a number following. This is the weight of the indicator that was applied for RICCAR. So at each level of aggregation. So at the exposure level, each of these indicators had a given weight, as well as at the sensitivity level, as well as the adaptive capacity level. Again, at the second level of aggregation was at the dimension level, so you'll see the weight of each dimension. And then ultimately which were aggregated together with sensitivity with, exposure with sensitivity. Each of them were weighted equally to develop potential impact. And then potential impact is weighted equally with adaptive capacity to calculate the vulnerability. At each level of aggregation, each of these weights should sum to 1. If they do not sum to 1, you will have errors. So make sure that the weighting of all of your indicators sum to 1. And if you check each of our indicators, you'll see that at each level, they sum to 1. So, we develop an impact chain at the very beginning as a brainstorming tool to assess which indicators, which facets of vulnerability you want to consider for your analysis. And throughout the course of developing your vulnerability assessment, this may change multiple times. It depends on data availability, something that you may have wanted to consider for sensitivity. You may have had data challenges, may not be available to cover your area study. The data itself may be questionable. So you will most likely update your impact chain multiple times before you have your final result. And it's meant to be interactive. To perform geometric aggregation, we'll again open up the spatial analyst tools. We'll open up the raster calculator, which is found under map algebra. And here's the same tool in Arabic as well as in French. You must have all of your indicators open in GIS, and they will automatically show up here once you open the tool. You can't add them directly to the raster calculator. They already must be open in GIS. And we will use the power function. If you scroll down here on the right, you will find the power function to be used. So the power function is determined, it will basically look like something like this in the raster calculator. So we'll say power, you enter your indicator such as population density, followed by the weight such as 0.14, and with a multiplication computational sign in between until all of your indicators included. You will then save your output raster as you see appropriate, shown here. As I showed you early on in this presentation, low vulnerability we tend to classify as in green color, and low adaptive capacity, low vulnerability is defined by low potential impact, which would be values of 1 to 10. Well, excuse me, low potential impact would be values of 1. But if you look at adaptive capacity, we look at it as in the reverse. And so for adaptive capacity, low values of 1, which would be over here on this side of the scale, in red, low would be values of 1 tend to be low adaptive capacity, whereas values that have low vulnerability would have adaptive capacity values of 10. So this is sometimes a challenging perspective to look at. You may have to look at our documents available from our website to kind of grasp a full understanding, but I did my best to kind of present it here graphically for people to understand. So again, areas in green are generally low vulnerable, whether it be low exposure, low sensitivity, and areas in red are high vulnerability, so it'd be low adaptive capacity, high exposure, and high sensitivity. And we designate this with the stoplight classification. So because adaptive capacity values are slightly different, areas in red are low adaptive capacity areas, in green with a value of 10 are high adaptive capacity. To aggregate adaptive capacity with potential impact, since the numerical values will be reversed, we have to invert for adaptive capacity. So the equation is, if we classify our values from 1 to 10, we would take the value of 11 minus the indicator with its weight. So if values were classified from 1 to 5, it would be 6 minus the indicator. We do not want to have values of 0, and they'll create challenges for aggregation. So they all should be valued of 1 or greater. So that's why if we had 10 minus the indicator, we would ultimately have a value of 0, which is not appropriate. So the minimum value of any indicator should be 1. So that's why we subtract from 11. So some key points to summarize on indicators in aggregation. They must be geospatially covered to include the entire area of study. You cannot aggregate gapped areas. At each level of aggregation, the weight should sum to 1, whether it be at the indicator level, the pillar level, the dimension level, or the component level. Again, pillars and dimensions may or may not be used for your particular study. You may have only aggregated the indicator level to components. But depending whether or not you use these aggregation, the weights should be done at each individual level. There are no ideal number of indicators. We had many indicators that we used to RICCAR. but don't feel compelled necessarily to use the same amount or close to the amount of the same indicators. You may be able to convey your message by only having 3 or 4 indicators for exposure, sensitivity, and adaptive capacity. So there is no right number as long as you're able to comfortably convey your message. Each indicator must be independent of one another, having weak or no correlation with one another. If you have strong correlation between 2 different indicators, it's effectively duplicating the indicator. So you want them independent of one another. All indicators should be in raster format to facilitate aggregation. For RICCAR, particularly a lot of our adaptive capacity indicators they were statistical data at the country level. So what we did was take the indicator values at the country level and match them with a geospatial data set of the Arab states, and ultimately to develop a shapefile which was converted over to raster format. So if you happen to have anything in shapefile format, they all need to be converted to raster. Otherwise, you will not be able to aggregate them with one another. The range of values for aggregation should range from 1 to 10 when you want to aggregate. If your range of values exceeds this or is less than 1 or greater than 10, there is an error in your aggregation. So that's a quick, easy way to check if you did a miscalculation or misrepresented your weighting. If it exceeds these values, it's a good sign that there's an error. Each of your indicators should have the same spatial resolution, and we'll look at this in a moment. So they should be indicators that have a spatial resolution, whether it be 1 kilometer or 10 kilometers or another value. They should all have the same spatial resolution. The way we do this for change the same spatial resolution, as we've been talking, for example, our climate data sets are at 50 kilometer resolution. We change the spatial resolution of these indicators by using what we call the resample tool. Resample is found under the data management, which if you were to scroll up in GIS, you'll see the data management tools. And then there's several tools under there. There's raster, and under the raster, there's raster processing, and here's the resample tool. Again, here it is the same tool in Arabic as well as in French. And this is how we would resample data. So if we happen to look at a climate data set, of course, they're in the 50 kilometer or approximately equal to 0.44 degrees. So here's the full, it automatically populates with the full precise decimal resolution, but more or less it's 0.44. So to change those, we would change the spatial resolution. If we were to change the climate data sets to 1 kilometer, it is approximately equal to 0.008, 8/1000ths. So that's for 1 kilometer. So we would enter these values, enter the same value for the X as well as the Y dimension. And we want those to be the same to maintain it as a square grid cell. Once we enter those values, we can select the different resampling techniques. Nearest technique basically just changes the cell size. It doesn't change the pixel values themselves. It would still look very closely like 50 kilometer data. You just happen to have smaller grid squares. And nearest is best for discrete data like land use. There's also a method called bilinear, which does some smoothing. It will interpolate the value of each pixel by using the 4 surrounding grid values. Cubic, which interpolates the value of each pixel by averaging the surrounding 16 grid values. And either bilinear or cubic is recommended for vulnerability assessments, depending on your best judgment. And lastly, there is what I would call as majority, which is also best suited for discrete data. So this would be not applicable. So you select your method, and from there, your results will be presented at a different spatial resolution and be suitable for aggregation. Another tool, once you aggregate your data sets, or even before aggregation, your GIS data sets maybe have a larger spatial area. So if we happen to look here, climate data, precipitation data that's classified, we may only want to do a vulnerability assessment at the basin level, for example, the Majerta River Basin. So we would basically clip the data set for both quickening of computation times as well as ultimate presentation of a vulnerability assessment map. So what we would do for that is we would use another spatial analyst tool called extract by mask. Mask would be the shapefile they are extracting to. It works similar to clipping, which you may use quite often in GIS. So it's instead of clipping for raster data sets, what we do is extract by mask. Here's where to find the tool. You extract by mask, for example, here's the input data set for precipitation. The watershed boundary is what we're masking to, the shapefile that we're going to match, and then our output raster. And once you do all of your work, you would ultimately present on a map. It is recommended to, again, use the stoplight color scheme method, whereas areas in green would happen to have low vulnerability and areas in red would have high vulnerability. This happens to be the map for mid-century for RCP 8.5 for RICCAR. And as you see, it's generally for the entire region, moderate, in these yellow, orange colors, to high vulnerability, such as these locations. And your high vulnerability locations can be, in turn, be considered hotspot areas. So if you look at our report, you'll see several maps for all of our different sectors, and they will look in varying degrees something similar to this. So for RICCAR, we ultimately decided not for the entire region to present results. What we did is highlighted the study area. The study area for water availability we defined as rangelands, crops, populated areas, and wetlands and forests. So, areas that are in the middle of the Sahara Desert may not be relevant in terms of water availability, either no vegetation, no population, etc. So we highlighted areas that were relevant to the sector itself. So you may not do this if you happen to do a study at a country scale or at a basin scale. You may not have these sort of gaps because all of your area is relevant. So this is what we happen to do for RICCAR. But ultimately, your map will look something similar to this. You should have, again, areas in green be low vulnerability, and areas in red be the highest vulnerability. I included an exercise for this module. I gave you temperature and precipitation data that's already been, it's the ensemble itself for mid-century RCP 8.5. I asked you to reclassify those values based on these ranges using manual classification. You'll see for temperature as well as for precipitation. Because these data sets are available at 50-kilometer grid, I ask you to resample to 1 kilometer. Then aggregate those indicators using these weights, 0.4 for temperature and 0.6 for precipitation. Extract the results based on the Majerta River Basin, which I gave you that shapefile, and then reclassify the output using equal interval and map using a color scheme. And the ultimate result should be something similar to what I've shown here. So you're definitely welcomed and encouraged to conduct that exercise. And as always, feel free to ask me questions. I apologize for going so much information, but again, our time limitation is very, very short. So feel free to shoot me any questions you may have later on once you've kind of had an opportunity to digest all this information. As a reminder, we have the resources available from RICCAR, which you can look at. Oops, that's wrong. Oops, I was showing the wrong slide here. These resources to look at, which will help define some clarity, and we are most available to assist on any vulnerability assessments you may wish to conduct. So with the remaining few moments, I'll ask Joelle if she has any questions she would like to relay to me.
One is about how to determine and estimate the difference in adaptive capacity between countries or between provinces within the same country, and more specifically, how to do that through GIS.
So the best way to do it, again, for our adaptive capacity indicators, most of them were from tabular data sets at a country level. So we paired the table with the GIS data set for the countries, and you can do that using the join tool. I apologize if you're not familiar with the join tool. I don't have a slide of what it looks like here, but if you have any questions on how to find the join tool or how to use the join tool, feel free to ask me a question. But they will help convert your tabular data to geospatial. It would be similarly applied if you happen to have a table of values for provinces within a country. You would pair that table with the geospatial map of the provinces using the join tool, and that will convert it over to geospatial. Thank you.
Marlene, we have a question about the aggregation at each level. If you can just quickly explain the aggregation at each level. Is it with the same way as it's done for the aggregation within each level, between each level?
Well, yes, you would use that aggregation, you use that raster calculator, you would calculate at each level. So, for example, if we look at the population indicators under sensitivity, we would aggregate these 5 indicators, first of all. And then once we do it for each level of each dimension of sensitivity, we would aggregate population with natural, with man-made. And then we would have sensitivity, and then aggregate again sensitivity with the exposure, and then aggregate potential impact with adaptive capacity to ultimately find vulnerability assessment. So you would definitely get very, very familiar with the raster calculator, because you just get to do it at each individual level multiple times as you go up to ultimately determine your vulnerability.
That's it for the questions, Marlene.
All right, well, I thank you very much for joining us today. As always, feel free to send me any questions. And I thank you very much for participating in our webinar series. If you happen to miss any of the sessions, they are available from our website on demand to use as needed. We are also happy to announce that Aksad, who is one of our partners in RICCAR, is developing an Arabic version, a mirror of these webinar modules, completely in Arabic, and they will have that available in the near future. It will only be done on demand, available pre-recorded on demand. but those will be available in the near future as well. So for those of you who requested these presentations in Arabic. So with that, I thank you very much for joining us. So again, thank you, and I wish you a good rest of your week, and hope to join you with a future session soon. Goodbye.